Another great question that we got, and how do we explain it, is dissolving. You might remember in year 12 that we said that like dissolves like. So that means that a non-polar solvent will dissolve a non-polar solute. So for example, you can dissolve iodine in petrol or cyclohexane or something like that. But for some reason, they won't dissolve very well in a polar solvent. Whereas polar things, like ammonia, will dissolve really, really easily in water, which is also a polar solvent. Then we also found that, well, polar solvents also will dissolve ionic substances because they've got charges and the polar solvent has got a permanent dipole. So it's got a slightly negative side and a slightly positive side. So those were our general rules that we learnt last year. But this year we have to explain why. Basically, this little phrase here, I'm sorry, it's a bit wordy, but it's the best I could come up with in a hurry, is talking about the relationship between the solvent and the solute. So the solvent has to have strong enough attraction to these particles at the edge of the solid to pull them out of that solid, out of the crystal. So it needs to break these bonds with the neighbouring particles. So it comes down to the nature of these particles, the nature of the solvent as well, the bond strength within the solid, and the bond strength between the solvent and those other particles. This is quite a lot to consider. I'll address this question at the very end because it's quite an abstract idea, I guess. So, if the solvent has strong enough attractions to these particles, it can rip them out of the lattice, and that is what dissolving is. Water will dissolve something like this. Is meant to represent sodium chloride, and it would be in 3 dimensions as well. So there'd be a chloride up here, there'd be a sodium up here, and they'd be linked to each other with an ionic bond and so on. Well, in here, we've got ions. They have got a really strong ionic bond, and in each case, multiple ionic bonds, and they're directional. So this shouldn't dissolve. But because they're only 1 plus and 1 minus, and because they're not the smallest ions in the world, they're relatively big, the strength of these ionic bonds, they're not the strongest ionic bonds they could be. If enough water molecules with their delta minus side, so the oxygen side, surround a chloride at the edge of the ionic crystal, the ionic solid, then they can form an ionic permanent dipole force. So these have got permanent dipoles, this is ionic. So we describe the force between these as an ionic permanent dipole force. It's pretty strong because you've got a delta minus, sorry, I've got this around the wrong one. Sodium it should be. Sorry, simple plus and minus mistake in my head. So they will make an ionic permanent dipole force. Ionic because this is a positive ion, and these have got delta minus, delta plus, so they've got the delta minus side surrounding it. Then what they do is they remove that ion that's dissolving. Then other water molecules, this time I will get it right, their delta positive side can surround in 3 dimensions, surround the chloride ion and rip that out. And so now we've got these particles that are ions surrounded by molecules in 3 dimensions. And they are held together by ionic permanent dipole forces. But they flow, they're able to move. So that's why it's dissolving, doesn't automatically go to being a gas or anything like that. So what we have to consider in this is the nature of our solute, the stuff being dissolved, and our solvent, the stuff doing the dissolving. If they can make a strong enough force or attraction between each other, then there is a pretty good chance that peripheral or outside ions, in this case particles, are going to be removed. And that is the process of dissolving. But they need to have a pretty strong force between them. Ionic permanent dipole forces are pretty strong. They are, you've got an ion in there, you've got a fully positive or fully negative charge there. And therefore anything with a slight negative or positive charge is going to be attracted to them. That's quite strong. Strong enough to start breaking, stretching and then breaking some of these bonds. By the way, when we do this, what we notice is that the temperature of this whole system goes down. That's because this bond breaking actually requires energy. And something we're going to get into later is about entropy or disorder. Doing this increases the disorder. So even though this is endothermic, it needs more energy. The strength of the bonds between the ions and the molecules is lower than between ions and ions. Because it's increasing its disorder, it's becoming more chaotic, it happens spontaneously for a certain amount of salt. I think it's about 350 grams per litre, which is a lot. If these are 2 plus and 2 minus ions, or even 2 plus ions and 1 minus ions, the solubility would probably be a lot lower because the strength of the ionic bond would increase, making it harder to remove those ions out just with an ionic permanent dipole force. So what about this? Why won't non-polar solutes dissolve in water? So I'm going to wipe this one off. This is why I haven't taken a photo, because I want to actually do a couple of different ideas here. If I have got my water molecule here, and if I have got my solute, just quickly making a solute, it's going to be a gas one, I'm sorry. So if I was to bubble ethane, I'll make ethane, so I can't bother making a double bond. If I was to bubble ethane through water, nothing happens. The ethane just evaporates out. And the reason for that is that ethane, which I'm very quickly making, is a non-polar substance. So it can only make temporary dipoles. So there we are, quickly made. There's my ethane molecule. 2 carbons, single bonds only, ethane. Okay. Water molecules come along and they rely on the size of its electron cloud to create temporary dipoles. And it will do that. It will definitely do that. Some molecules will have a slightly negative side and a slightly positive side. And so what they'll have is a permanent dipole from the water and a temporary dipole from this, a permanent dipole, temporary dipole force between them. So let's say, for argument's sake, that this end of the molecule at this moment is slightly negative. So this end is slightly positive. Whoops. That would suggest that this side of the molecule, the slightly positive side of the molecule, could be attracted here. The problem is there's other water molecules hanging around and saying, actually, be attracted to me instead. And the hydrogen bond between these, or even the permanent dipole forces between these, is going to be a stronger attraction than to the solute. So because they're more attracted to each other than they are to the solute just evaporates off, disappears without dissolving. And that is why non-polar solutes won't dissolve in things like water, which are polar solvents, because the attraction between the particles is not enough to overcome the relationship between the solvent particles. So their attraction is too strong to get interfered with by a molecule that is non-polar. The force, the temporary dipole, permanent dipole force is not strong enough to overcome the permanent dipole forces in liquid water.